Welcome! In this video we will look at the graphics control and the use of masks to create maps with the PowerBasic Windows Compiler. This is where we left off at the end of the last video. We had a dialog on screen with a graphics control and 3 hexagonal masks displaying on screen, showing the fact you can have masks which effectively don't overlap each other. What we're going to do today is we're going to extend on this to produce a full graphics map. Now there are a few things we want to do to set this up. We're going to set a couple of constants up that will define the size of our grid. We're going to have a grid that is 10 hexagonals wide and 5 hexagonals tall. Now in our last program we generated the terrain randomly, but we weren't doing anything to save it. Every time we ran the program it would generate an entirely new map. Now we want to set up a global array to actually store the values of the terrain we're actually going to be displaying. And this long global terrain we are going to dimension in our main function. And we'll use the constants we have set up. And we're going to make this a 3-dimensional array because we want to store the x and the y coordinates of the top left-hand corner of the mask we're going to put onto screen, and we also want to, in the third element, store the value of the type of terrain. Now we have at the moment 3 different types of terrain, A, B and C, plus our mask. We're going to copy in a couple of new types of terrain. We'll make these D and E and we'll make them different colours. So having set that up, the other major change we're going to make is to the dialog itself. Now the dialog when we created the last one was a fairly basic dialog onto which we had added our graphics control. What we're going to do is we're going to use a new option called pixels. Now if you look at your dialog new in the help, there are a number of options. The default option for dialog is for dialog units. Now we're using the pixels option. Then with the pixels option, all size and position parameters for putting things onto the screen are actually specified in pixels. There are advantages to both options. The pixels option we're going to be using because we want the exact location on the screen onto which to put our mask. So having said that, if we have a look at our event handler, the callback function, this is where we called our routine to build the graphics. Now I'm going to comment that one out for the moment because we're basically going to recreate that function. We'll leave the original one there so we can refer to it. Now there's a couple of things we'll do before we actually call the build graphics map function. We'll want to specifically put an attach command in for our graphic to attach it. And we'll put in the handle to the graphic. And we'll mark it for redraw. And we're going to make this a black background. Now the reason for the graphic attach command is that we may be attaching and reattaching different graphic maps during the course of this program. So we'll specifically attach it here so we know which one has actually been attached so we can actually draw to it. Now let's go and we will create our build graphics map. We'll put this one just above the previous function, as its parameters are going to be exactly the same. Many of the variables we're going to be using are exactly the same, so I'll just paste them in for starters and we'll cover them as we go. The other thing we're going to use is we're going to use the randomize command to make sure that our random number generator is as close to random as we can possibly get. Now we're going to set some of our variables here. The x and y are where we'll start on the screen. 35 coordinates in and 15 coordinates down. coordinates in this case are pixels. And we're going to set a standard width of 28 pixels and a drop of 28 pixels. And I've also created a couple of variables to handle offsets for the hexagons. As you can probably guess, it took a while to get this calculation just right. But as we did before, we're going to have a for next loop to step through and create our hexagonal map. And since we're driving it by these constants, we can tweak the size of our map just by changing the size of the constants at the beginning of the program. So we're going to run through each element in our array, and we will work out the top left hand corner of the first polygon to be actually displayed on screen. And since we want to use our offsets, we want to work out whether just as we did before, we need to work out that we have to offset the hexagon for each alternate column. This adds slightly to the y coordinate. And then we will pick up the starting position, the y coordinate of our polygon, based on the long temp variable. And then by the time we get to the end of that, we will have our locations. This is where we want to start placing our bitmaps onto the screen. Just exactly as we did before, we will pick up our bitmap mask from our graphics folder, and we will work out the size of the bitmap from that file. This is exactly what we did in the previous one. Now, we're now using a random function to pull back a value between 65 and 69, which is basically A to E, which are representing our hexagons. And we're storing that in a long terrain variable. Now we'll want to store this value so that it gives us the option at some point of actually saving this array to file. You can of course load it back up later on. And having got that value in the terrain variable, we're now storing it into our global array in the 0 element. The 0 element is for the number between 65 and 69 of our terrain. Now, since we've got the x and y start coordinates, one thing I want to do is I want to store the center of those hexes. Now, since effectively we're putting a square on the screen, then the x and the y coordinate of the center of the square is equal to the top left hand corner plus the width divided by 2. Simple way of working out what the center of the square is. You'll see why we're storing this very shortly. Our next thing to do is to load up the bitmap for the terrain type we've decided on, and since we stored that in the long terrain between 65 and 69, $$ will give us the letter between A and E, and that defines the bitmap we're about to load. And we use the graphics bitmap load command, just as we did before, to load up the bitmap for width and height to our mask, and the bitmap width and height to our bitmap handle. And then just exactly as we did in the last video, we will use the graphics copy commands, first of all to copy the mask onto the graphics control, and then on top of that to merge in the actual bitmap. And having finished with our bitmaps, we will free up the memory using the graphic bitmap end. Now, if we just try a quick compile to make sure we haven't missed anything, which we have, we've missed a comma. Right, okay, let's run that program. Right, we need to make the dialog slightly bigger, but we can see all the hexes appearing quite nicely. So we'll increase the size of our dialog and the size of our graphics control. So let's push this up to, say, 790. for, let's say 500. And our graphics control we'll make a bit wider, make that about 750 by say 460. So let's try that, see how that looks. That gives us a bit of room for expansion. So what we have now is we have a much better method for displaying all our graphics. They all appear quite happily on screen, with the terrain types between A and E. So having got that on screen, this is the beginnings of our map. What we want to do now is we'll want to label the columns and the rows so you can identify where each of the hexagons actually appears in our global array. So we go back to our routine and we're down to this point just after where we've cleared off the bitmaps. Now we want to set up the grid IDs. For our first column we want to put in the row. So for that we're going to use the graphics set position command. And in there, since we've already got the coordinates for the X, and we will tweak the Y coordinate slightly. Now I'm using the integer divide here. Integer divide means it will divide long drop by 2 and it will not give you anything after the decimal point. And then having worked out what position we want to actually type at, we'll use the graphics print command and we'll print the long C. So if we try running that, what we will get is the 1, 2, 3, 4, 5. So this is the 1 row, 2, all down to 5. So having done that on this side, we want to do it on the other side as well. Exactly the same kind of approach. The only difference being we're going to use the max X. Well, that's cool. Our graphics color can be exactly the same. Our position will have to be slightly different. Now, the Y coordinate is going to be exactly the same, but our X coordinate will be slightly different because we don't want it on the left hand side of the hex, we want it on the right hand side of the X. So we need to add an offset onto that. So let's try that. And there we have. Now, the idea of putting the number at the bottom side of the C and the bottom side of the A, so you can quite easily work out which row that is on. And the numbers are far enough apart so there's no confusion. All we have to do now is to label the columns. We can do this one more or less the same way. Two different conditions, one for the first column and one for the last. The same kind of logic. And putting in specifically setting the colour each time, just in case we're going to introduce routines later on that will actually change colours. So for the first one we need to work out location, so we need to use the graphics set position command again. And again it appears in brackets. And all we have to do is to work out the actual location. Now for the first one we're basically using the X polygon. And we'll add a few pixels on just to give us a little offset. And we want the Y polygon. And again we'll do an offset on that one as well. and we'll want the graphics print command, and this time we're going to be printing the long R, but we want it as a letter rather than a number, so we're going to add on X letter. Now X letter starts at 64 and works up, so the first one will be 65, which is the letter A, and rather than format we're using CHR dollar because we're turning this number into a character. And we'll do exactly the same thing at the end. The only difference being our coordinates will need to be offset slightly. So we'll want the polygon X plus 6. And our Y coordinate we can offset slightly. And we'll add on the height of the actual box. And now that should position all our letters correctly. Unfortunately it's not. What have we missed? We haven't set the value of X letter. That's a problem. It's the one that should be 64. So let's just slot that one in. And we'll run this now. Right, there we go. So we can see this hexagonal is A1. This is B1. This one down here is J4. And this one here is in the column E, and the closest number to it is 3, so that's E3. Now that's all very well displaying on screen, but the next thing we want to do, we want the ability to be able to actually work out if the user clicks on one of these hexagons, which hexagon they have actually clicked on, what its coordinates are, and what terrain type is actually underneath it. So we need some kind of event handler to handle the mouse click. So how will we do that? Well, it'll have to be in the event handler, but one thing we'll have to do is we have a look at the graphics control. There are no options on the graphics control here, so one thing you'll want to do is nip into your form designer, have a look at your graphics control, and under styles there's a notify option which you want to tick. This means whenever the user clicks on that control, then a notification is sent to the payment, in other words the form itself, and you can handle that in your event handler. There is our notify command there quite happily. So now if we go to the event handler, our callback function, we need to put something in here for the graphics control. That's better. Now this will handle picking up of a click event on the graphics control. But we don't want to pick up just a click event. We want to work out the coordinates on the graphics control that the user has actually clicked on. My idea in doing this video is to use many of the out-of-the-box commands that PowerBasic supplies for the use of graphics controls, and to avoid Windows API calls where possible. Unfortunately, we're going to have to use a couple of Windows API calls here because the graphics control doesn't actually provide a method by which we can pick up the X and Y coordinates that the user has clicked on. So we're going to need a couple of variables on our callback function. We're going to need a graphic as a handle. Now we'll want this one static as it's not going to change during the duration of the program. And we'll want another one which is going to use the point type. So right down here, after we have our build graphics map in our initialization part of the event handler, we want to put something in to get the handle for the graphics control. This is the Windows handle. And that's what our hgraphic is for. This gives us a handle to the actual graphics control that we can call Windows API calls with. And further down here, on our click event, that's exactly what we're going to do. We're going to call a Windows API call called getCursorPosition, and we're going to pass that to our pLocation variable we set up earlier. Now that will give us the cursor position in pixels of where our mouse actually is. Now we want to turn that into a location that's relevant to the screen we're actually on. And this Windows API call will do that quite nicely for us. Now this will actually give us a location, X and Y coordinates, on the actual graphics control, which is exactly what we're after. Now the other thing we'll want to do is, just so we can see where we are, let's put a status bar down at the bottom of our screen. Just something we can actually put information on so we can see what we're doing. Right, okay. Now having got our X and Y locations, we can set the text on that control. And we called it IDC. And we're going to display the X coordinate. And we're going to display the Y coordinate as well. So if we do this now, there is our grid, and if we click on one of the coordinates, our coordinates are quite happily appearing at the bottom of the screen. Now that's all well and good, but how do we turn that into exactly which hex has the user clicked on? An interesting dilemma. So our hexagons on screen have a top left hand corner, and we've already stored the center of the hexagon, so we know the coordinates of the very center of each of these hexagons. So when the user actually clicks somewhere on the screen, what we need to do is we need to work out basically which of the centers of each of the hexagons is actually closest to the point on which we have clicked. And this is where we use Pythagoras' theorem. That day in school, when the teacher explained that one day you would have a need for Pythagoras' theorem, today is that day. So what we need is a function that will go away and actually work out which of our hexes we're actually on. And we'll display that just like we displayed everything else on our screen. We'll call this getHex. Now we're passing it our two locations. We're passing it rather our two coordinates, X and Y coordinate, and its job is going to be to work out which hex are we actually on. And we'll return a string because it's going to be something like A1, A5. So this is a very useful function which we can use to work out the actual hex the user's clicked on. So we can use that for picking up information for what terrain they're on, where the unit might want to move. So first thing to do is to create some local variables. So we're going to use the distance one to work out our distance. Another variable to work out what the shortest distance is. We'll use a string variable to work out which one we've actually found. And we may want to actually set our shortest distance. I'll need to have a value first of all, because it would initialize as 0. So if we make it some ridiculously big number that's bigger than anything we've actually got on screen, and now we need our for next loop. And this is going to loop around our entire global array and work out which is the closest hex. So what we need to do is our Pythagoras theorem. Now we know that our global arrays hold the information we're after, and the x coordinates stored in there, and the y coordinates stored in the second element. Right, so our coordinates coming in, we'll set these up. Call this long x, and we'll call this long y. So since that's the coordinates that come in, we'll take the long x and we'll subtract from it the value we've got in our first hex. Now if this gives us a minus figure, we don't want the minus figure, so we use the abs command to turn it into the absolute value, which basically loses the sign. So if long x minus the train value is minus 5, it comes out as 5. So we basically want to square that value, and we're going to add on to that exactly the same approach for the y coordinate. So we're getting the square of that one, and we need the square root of the whole thing. Assuming I've got all my brackets in the right place. Yes, that should be it. Now, having got the distance to the square, or to the hex we're actually looking at, we need to work out whether the distance is shorter than our shortest distance. And if it is, then we will store the distance in the shortest distance. And we will store in strFound now we'll bring back the value. We'll store the column and the row. For example, A1. And we will add on to that what kind of train we found. And we know we stored the train in this terrain array as well, which is stored in the 0 element. And we know we have to turn that into a letter. So what we should have here is we should run through every hex in our long train array, work out the distance between what the user has actually clicked on, coming by the x and y coordinates, working out which one's the shortest, and by the time we get through this entire routine, strFound should have in it the hex which is the shortest distance. Then all we have to do is return that in a function. So assuming we haven't made any syntactical errors, which we have, I missed? Oh yes, I've missed the end if. And if we run that now, and again another one, what have I missed? I need a bracket around that. Yes, that looks better. No, not quite there yet. Not quite there yet. Yes, there's an extra bracket needed in there. Right, I think we're there. Okay, now we have a map on screen. So if we pick our first hex, which is A1, and click anywhere on the hex, it comes up, the coordinates, it's also identified when we clicked on A1, and tells us it's terrain type D. So we try one on the far side, it comes up J1 and it's terrain type E, pick one in the middle, F3, which is correct, and it's terrain type C. So this is quite happily picking up, regardless of where the user actually clicks. Even if they click way in the corner, it's still picking it up correctly as H3, which it is. So we now have a method by which the user can actually click on any of the hexes, and the program can, underneath the hood, work out what they've actually clicked on. This can be used to set positions of units, to set destinations of units, or to do anything we need to do to click on the map. And if we need to increase the size of the map, all we should need to do is to change the size of our max X and max Y variables. Make it a little bit bigger. And our map fills the graphics map quite happily. And our clicking will still work regardless of how big the map actually becomes. So we're very close here to having a working map, and you can put your own graphics on the hexes to get it to anything you need. That's it for today. Thank you for watching.